So a bunch of primitives are hanging out on a video call, let's say Zoom, and there's some integers, some strings, maybe some floating points, and whenever like our integers would try to speak, somebody would mute them. And but there was this string who was really loud, and nobody could shut them down. You know why? Because they were immutable. All right, welcome to another week of Coding Interview Weekly. Yes, I'm still calling it weekly, even though it's been probably a few weeks already. But I've been busy with some stuff, better late than never. So this week, I'm trying to discuss this problem. Anyway, before that, if you're trying to figure out what this is all about, just you can go check the channel or this website out. Basically, I'm trying to record a bunch of videos, sort of tutorials, where I talk about a common interview problem, which you may find in any Google interview or like any other fan interview. And I walk through the solution at the same time, give you some insights into how interviewers think, what are they expecting from candidates, and those sort of things. So this time, the problem that I'm trying to discuss is pretty easy to state actually. Like, you just gotta say you have two strings, A and B, and you're trying to find the longest common substring between them. So essentially, what that means, what a substring is, it's basically a part of these two strings which matches. So you have this substring from position I to j, let's say, and you have this uh, substring from I2 to J2, and we are essentially trying to find a substring which is longest. And that's it. That's the problem. So before I jump to the solutions, why don't you just take a pause, think of the solution, starting with the most brute force solution that you can think of. You don't have to worry about time complexities from the beginning of the interview itself. So treat it like as a real interview and just start out with thinking out loudly, and I'm gonna help you with that. So the most obvious way is, let's say we hypothesize that the common substring starts at position I in string A and at position J in string B and is of length K. So essentially what we are saying is A of I to I plus K is equal to B of J to J plus K, right? That's our hypothesis. Now, a pretty simple way is iterate over I, all possible values of I, all possible values of J, and all possible values of K. And to determine whether these two strings are equal, you can just simply iterate over both of them. That's a good start. And what is the time complexity of the solution? I has n possible values, J has n possible values, where n is, let's say, the size of both the strings. K also has n possible values for each I and J in the worst case. And then these strings, these substrings, both could be of size n in the worst case. So we are looking at an order of n raised to 4 solution here, which is a good start, I would say, but there's a lot of scope here of improving. So let's get down to it. The first observation that we need to make is, let's say we represent f of I j k as true or false, denoting whether there is a substring of length k. It starts at position I in string A and at position j in string B. We are trying to determine f of ijk for all possible values of ijk, and then basically our answer is the largest case such that f of ijk is true, right? The observation which we can make for optimizing the time complexity of the solution is that if f of ijk is false, what can you say about f of ijk plus 1? Obviously, that's false too, because since the first k characters don't match, first k plus 1 characters cannot match either. So that's basically our recursive function that we're trying to devise here. So if you think about it, it's sort of a dynamic programming, it's turning into a dynamic programming solution. And that is a good direction to go into. So we are saying that this is essentially what? It's f of I, j, k. Take an OR with a of k equal to b of k. Actually, this should be k plus 1, right? We are saying that this is true only if f of ijk is true. Oh, actually, this should be an and. My bad. Yeah, this is true only if the first k characters match and the k plus 1th character is also same. So this is a simple recursive function, and the time complexity of this would be, as we know, like for dynamic programming solutions, it's number of different states multiplied by the cost of the transition. Here, the transition is constant time, and the total number of states is basically n cubed. So that brings it down to order of n cubed. Now, let's see if we can do even better. So if you remember from one of the previous videos where I talked about dynamic programming, uh, the simplest way to come up with solutions is just start coming up with dynamic programming states. This is one of the states where we say f of I j k denotes blah, 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 and come up with a recursive solution such that it optimally covers all the cases. So to optimize the time complexity, we need to come up with a state which is, we need to come up with a recursive function which is less number of states. So let's say we want to get rid of k from here, which is essentially hard coding what the length of the substring is going to be. So we are saying, let's say we denote f of ij as an integer, and it basically denotes the length of the longest common substring that ends at position I in string A. Basically, let me present that visually. So we are saying there's a string which ends at position I, and there's a substring which ends at position j in B. We are saying what is the longest length of that substring? And our answer in this case would essentially be a maximum of f of ij for all possible values of I and j. Now what we just need to do is try and figure out a recursive formula for this dp function. And how do we do that? So think of it like this. If a of I is not equal to b of j, then we don't have a matching substring which ends at position I and j. So in that case, our answer is 0. So we have two cases. If a of I is not equal to b of j, then our answer is 0. Otherwise, let's say they are the same. A of I and b of j are same. In that case, we need to look at the remaining characters in string A and B. Basically, one, okay, else it is one, we are counting these two characters, the matching characters, plus f of I minus 1 and j minus 1, right? And in this case, the transition cost is constant, and the total number of distinct states in the dp function is order of n square. So we have reduced the time complexity to order of n square here. So, what do I expect from a candidate who sees this problem? I would expect them to reach at least this order of n squared solution within 5 to 10 minutes, essentially, because ideally we would want to explore some more efficient solutions as well. Like this is a pretty good solution, dynamic programming. It shows me that you know the fundamentals and you have used some basic observations. You have improved upon the brute force solution, but this in itself is not really the best solution, and we can do certainly better. So for a candidate who comes up with the solution, implements it without any flaw, I would say they may get a leaning higher, but it's not a strong higher decision for sure because um, this dynamic programming solution, even though it requires insights and creativity, this is not the hardest DP problem you would ever see in an interview. So let's see how we can do better. For that, what I'm gonna do is get rid of this stuff. And the reason why we can do better, there's a very simple observation to be made. And but the thing is, uh, after that, we may need to use some advanced techniques, and I'm gonna talk about it soon, why those techniques are a little bit advanced. So the simple observation here is, okay, before we talk about observation, I want to say that that technique is so fundamental and we use it almost every day. And it's called binary search. And how it is applicable to this problem and how to generally apply it to different problems, I'm going to talk about that. So in this case, the observation, if you remember, we made was that if there is a substring of length k, which is present in both of them, then there is also a substring of length k minus 1, which is present in both of them. And that substring being, you can choose this one or this one, right? So there is something very special about this question that we are asking. And we need to rephrase it. So the question we are asking is, what is the largest substring present in both of them? Maybe we need to rephrase it and say that for any given k, can you tell me whether there is a substring present of length k? And if you can answer that, you can apply this technique called binary search. So when is binary search applicable? It's applicable when you're trying to find the tipping point of a binary function such that it goes like this. So let's say you have 0 and you have 1. And it's generally applicable elsewhere too, but I'm talking in context of this problem. So if you have a function f which goes like this, using binary search, you can say where does it stop being 1 and become 0. And how that applies to this problem is you are essentially asking for different k's whether a substring of length k exists or not. So let's say k is on x-axis, and on y-axis is this function called f, and f of k denotes whether there exists a common substring of length k. So f of k is either true or false, and we notice that for some value of answer, which is our answer again, for some value of answer, all the f of k's are true before that and false after that. So this is our answer. Now, this is a very common technique which can be used across many different problems, and I'll give you some examples on the website, lalitkundu.com. Um, this technique is applicable wherever you can rephrase the question in such a way to a yes or no question, and the function to which you are asking yes or no to is a strictly increasing or a strictly decreasing function. Actually, not strictly, but decreasing or increasing. It doesn't have to be strict. So for example, this is not strict. So let's say a function is like this, and you're trying to find the first point where it exceeds some value. Then you can apply binary search. And the reason why I say it, this algorithm is so hard-coded in our heads as well. We use it everywhere. Like, oh, am I speaking too much? Oh, oh, maybe not. Let me speak a little bit more. And we ask ourselves, am I speaking too less? Well, that's true. So let me speak a little bit more and stuff like that. So we apply it everywhere in our lives. It's sort of a calibration that we are doing. So how we do that in this case is you say, let's say you hypothesize about where your answer is. Let's say you hypothesize that your answer lies here, and you do this yes or no question, like do we have a substring of length k, which is common in both of them? If the answer is no, you recalibrate and come this way. And now if it's true, you say that actually let me try the next one too, and so on. So the good thing about this algorithm is that it divides the search space into half. With every question we ask, this is our search space from 0 to n, and we are breaking it down by half every time. So it's just gonna take log n questions at the very most to find this answer. So that's basically the crux of binary search. Now, how does it help us in this problem? It may be possible to calculate f of k efficiently. If you remember f of k being the true or false, denoting whether there exists a substring common of size k in both of them. And how we can efficiently answer that requires this technique called hashing. So hashing is basically a technique by which we represent large amounts of data into fixed length. We convert it into fixed length data and store it. It's very widely used for information retrieval in storage systems, as well as obfuscating data. So I'm gonna quickly talk about what that technique is and how it works. So what we are basically saying is you have a string. Oh, what just happened? Okay, you have a string. Let's say A, B, G, X, Y, blah, blah, blah. And you're trying to convert it into a fixed length data. And that data is going to be in an integer form. So what we are trying to do is convert the string into an integer so that every string can ideally map to a unique integer if possible. But that's not possible. If that's not possible, we want to reduce the collision probability. So how hashing works is you have a string and then you have a hashing function called f, and then you have the output. Output is integer, as I said. So, and we have different strings. Let's say this is s1 and then you have another string. They enter the hashing function outputs an integer. And ideally we want all strings to be mapped to different outputs. So how is this useful is that it's useful for making comparison. So we say that if f of s1 is equal to f of s2, we want to devise a function f such that s1 is also equal to s2 if this is true. And for that, what we do is imagine every string as an integer written in base 26, assuming that it has 26 different characters, let's say lowercase English characters. So imagine that it's essentially an integer written in base 26. And what we can do is convert it to decimal form. So how would we convert this to decimal form? Let's say A maps to 1, B maps to 2, and so on. C maps to 3, Y maps to 25, Z maps to 26. So how will this get converted to decimal? It would be, let's say this is string S, and these characters are S1, S2, and Sn. It would be S1 plus 26 into S2 plus 26 raised to power 2 into S3 and so on. Now, if we represent all strings in decimal form like this, they're pretty unique. Every string is unique. But the thing is, these integers in decimal form would be huge because these strings can be huge themselves. So the technique we're gonna use here is take a modulo with, let's say, 2 power 64 in a language like C++. And how that helps us is that when we take a modulo, these decimal integers, they randomly get distributed through the whole number line. And how that helps is, let's say you have a string of length 10 power 5. That means you have 10 power 10 different substrings, and all of them randomly gets distributed across this whole number line. So the probability of collision is 10 power 10 by 2 power 64, right? And that's pretty rare. If you want to make it even rarer, take another hash with another number, for example, and that basically reduces the probability. It's now you take a it's this raised to power 2. So that makes it even rarer, but usually taking modulo with one number should be enough. So let's say we have this function f. How is it going to help us answer the question, if you remember, was is there a substring of length k which exists in both the strings? How that's going to help is we have a fixed k. What would we do is for a and for b, what we'll do is for all substrings of length k, we'll generate the hashes for each of them, put them in a bag, b of a, do the same thing for b, put them in another bag called b of b, let's say. And now we're trying to say that do we have two integers? Do we have the same integer in bag A and bag B? For that, what you can simply do is take a hash set or just an unordered set in C++ and iterate through elements in one bag and see if it's present in any of the other bags. So that's like in order of size of bags, you can determine whether an integer is present in both of them. But the challenge being, how do you efficiently calculate the hashes of each of these substrings without iterating through all of them? If you iterate through each substring through and through, basically, that's gonna be order of n squared because uh, let's say the length of the substring is n by 2 and you have exactly n by 2 of those. So you are doing a lot of repetitive work. And for that, the technique, which is famously known as sliding window, Rabin-Karp, I mean, you may have heard a lot of names, but it's pretty intuitive to come up with by yourself too. And the observation being, if you have a hash of this first substring and you're trying to calculate a hash of the second one, notice that we are adding a character at the end and getting rid of a character from the beginning. So what we need to do is from this, subtract S1, divide the whole thing by 26, right? Now what's left is this, 26 raised to 1 and so on, and add 26 raised to power, and now add 26 raised to, you can figure out the exponent depending on what is the length of the substring, and just take a modulo. And now you have the new hash essentially. So you're reusing some of the work that you have done for these characters. And that enables you to calculate a rolling hash. It's called a rolling hash because you're removing characters from the back, adding some in the beginning of each of the substrings. And this reduces down the complexity of calculating each of these hashes to order of n in the worst case. Now, what does it mean for our overall time complexity of this algorithm? let's try to analyze that. Before that, I would say string hashing is slightly advanced technique, but it's quite ubiquitous, and I expect candidates to know about rolling hash and their applications. So if a candidate comes up with this by 20th minute, that's a pretty good hold they have over algorithms. And if they do the complexity analysis well, that's a good hiring candidate. Common mistakes, I would say, would be just like going into the brute force solution, and there are some implementation mistakes where if you literally divide by 26, that's not right because we are doing modulo arithmetic. So if you don't know about modulo arithmetic, you're gonna get stuck here for sure, because we're taking modulo 2 power 64, and then how division works is you need to apply Euler's, actually, Fermat's little theorem, and I'm not gonna go into that, but I'll provide some resources on that. So implementing this is pretty tricky. And if the candidate doesn't know modular arithmetic, it's probably okay. But just the basic idea is not dependent on modular arithmetic as such. It's just about hashing. And I would even allow them to abstract out this whole function f in the implementation, which calculates the hashes. But if they know modular arithmetic, that's icing on the cake. Um, okay, what's the overall time complexity? So you have order of log n, that's for the binary search, and each for answering each question of the form, do we have a substring of length k, which is common. We are going to apply this rolling hash and iterate over the whole string at least once, both of them, order n, and then whether checking the presence of an integer in a hash set is constant time. So the overall time complexity here is order of log n into n. Actually, now that I think about it, yeah, you're right. Yeah, I'm right. Okay. So that's the overall time complexity, and that's pretty good. I mean, that's kind of amazing. Big, if you look at it from where we came from, like from n raised to 4. And there's actually even a better technique, which I don't expect any candidate to know, which is using suffix automaton. Uh, it's an advanced technique, and if there's interest, I can try to explain that in a future video. But from a programming interview perspective, it's not expected. Maybe if someone took an advanced algorithms course, maybe I would try to take them in that direction, but usually not. Like if you have reached here, that itself is a pretty big deal. Implementation is tricky as well. I would look out from what I expect from candidates is to abstract out some of the details and functions so that we don't have to jump into implementing those and we could save some time. And those are some generic tips you can apply to any implementation. So that's it for this week. I'm gonna come up with a new problem and pretty soon put it up on website. So go check it out and leave any comments if you have any questions. I'd be happy to follow up. Thanks.